Welcome to my presentation. Again, my name is Michalis Kantartjis. I go by Mike. I'd like to thank you all for being here. Presentation will cover a comparative evaluation of univariate and bivariate choropleth maps. I've had this to present this for my dissertation defense and a colloquium very recently. This is by far the most abbreviated version of it, so forgive me if I leave out details. I'm happy to talk about it after the presentation. So in a nutshell, the objective was to rethink the way we engage with simple bivariate choropleth maps through the lens of COVID-19. Why COVID-19 and why bivariate maps? Well, maps were everywhere during the pandemic, and they were each telling their own story. And I thought, wouldn't it be powerful to show the effects of vaccination in curbing mortality? That's where the bivariate scheme piqued my interest. In my literature review, and full disclosure, I am an informaticist, not a geographer or cartographer, but thank you for having me here. I discovered that for the most part, bivariate maps were classified as expert or scientific maps, and that they were hard to read or use. I personally didn't buy into that, so I wanted to reevaluate bivariate choropleth maps through a comparative usability study. I also introduced an interactive feature hoping to improve their readability. And lastly, leveraging eye tracking, I wanted to explore the differences in visual search strategies and patterns when interpreting these types of maps. We recruited 75 participants from the greater Iowa City area and placed them into 3 interface groups. The juxtaposed univariate choropleth map, which we would call univariate because it's a mouthful, a bivariate static choropleth group, and a bivariate interactive group, which included the hover and highlight feature. As a between subject study, each participant only got one type of map. Each group had to complete 4 types of map reading tasks. The first one asked for specific information, which required participants to identify the values of a particular county. The second task required to search for objects given relative values, so find a county on the map with high variable X and low variable Y. The third task was to view the entire map and determine overall patterns regarding the 2 variables, so a general information question. And the fourth task, which was anomaly detection, asked to look at the entire map and select a county that differs from its surroundings. Our 2 main performance metrics were really just accuracy and efficiency, so response time. From an accuracy perspective, both interface groups performed well across all tasks, except for the anomaly detection, where the bivariate static group performed slightly better. So let's investigate why. Going into these experiments, we created bounding boxes, which allow for eye tracking data to be assigned to specific regions of the interface. For example, here we have map 1, where we assigned the vaccination and tree coverage data, which was simulated, and map 2, where we mapped mortality or case fatality rate and air pollution data, again simulated, along with their legends. This allowed us to better understand what types of attention transitions occur between the interface elements and how they may differ between correct and incorrect responses. Which brings us to the transition probability matrix. It can be a little difficult to read, but essentially, if you are looking at a specific interface element, let's say the task instructions, what is the probability of looking at another element, let's say another map or the legend? So again, task 4 asked participants to select a county that differed from its neighboring counties. On the right, we have incorrect responses, where participants were more likely to navigate to the bottom map, as we can see here highlighted. From any of the other interface elements with frequent transitions between the 2 maps. In correct responses, participants had a similar pattern. However, they spread their attention to the top map as well and overall engaged more with the rest of the interface elements. The pattern in the bivariate group was even more obvious. Correct responses transitioned between the legend and the map more often, also glancing at the map legend and the variable labels. Incorrect responses did not register any label fixations and mainly focused on transitioning between the task instructions and the map, with little attention to the legend. We see this pattern more distinctly in scan path plots, with frequent back and forth movements between the univariate maps, whereas the bivariate maps required less overall transitions. I included this graph to highlight the low performance of the first trial of the first task in the Bivariate group. Let's look at why. Remember, in task 1, participants were asked to retrieve the values of a specific county and select a multiple choice answer that best fits. Incorrect responders focused on the first variable listed in the answer choice, and they paid little attention to the second one. Correct responders also, whereas correct ones paid attention to both variables. Correct responders also paid close attention to the axis labels on the legend, whereas incorrect responders searched the legend more to match the colors with the appropriate county. Let's now look at response time. Overall, the Bivariate group was faster in tasks 2 and 4, but had similar response times in tasks 1 and 3. So in task 2, we asked to identify a county with high air pollution, greater than 5, and high tree coverage, greater than 20. The Bivariate group focused on the legend, focusing on the axis labels and identifying the representative color, which is the upper right quadrant. The Univariate group had to split attention between the two maps in their legends, essentially having to repeat that action. Interestingly, in task 1, participants derived values from a specific location and had similar scan patterns between groups, so both in the Univariate and the Bivariate. So answer choices to county, to legends, back to the answer choices. In task 2, however, the Univariate group showed more scattered back and forth between the maps, whereas the Bivariate group followed a distinct pattern again. Instructions to legend axes, to the appropriate color, back to the answer choices. So what about interactive hovering? All this was a bidirectional highlight between the legend and the map. I also added a tooltip with the color-coded descriptions of the variable groups. With this functionality, participants could also highlight a county on the map, and the corresponding color would be highlighted in the legend itself. So in this analysis, we compared the same Bivariate static group to the interactive one. So starting with accuracy, we see pretty similar results across all tasks, yet in the anomaly detection, we note how an interactive group performed statistically better. That was surprising given how similar accuracy was in the other tasks and how similar the interfaces are. So let's look at why. Here we have the aggregate gaze heat map of the anomaly detection task with COVID data. On the left, non-interactive users relied less on the legend and more on searching the map itself. On the right, interactive users paid more attention to the legend, with some fixations on the tooltip as well. So somehow in this task, the interactive tooltip and the highlighting allowed for a more focused attention on the legend. We noted again poor accuracy in the first trial for the interactive group as well, with again, accuracy improvement in the following trials. So let's look at what participants were doing right or wrong. Correct responses were more likely to transition to the legend from other interface elements, while incorrect responders were more likely to transition between the map and the instructions. This is again the Bivariate group. Correct responders were more likely to look at the legend values and labels and then transition to the answer choices. We hypothesized that this might be a pattern that was used to verify axis labels from the legend and values with the appropriate answer choice. So looking at the correct responses, there's a greater density of fixations on the axes and the variable names. These fixations often transition directly to the answer choices, making sure to match the legend labels. Incorrect responders had fewer fixations on the legend and on the legend labels and had fewer transitions between the labels and instructions. This pattern was again similar in what we saw with the Bivariate static group. So overall, we found a significant increase in the number of correct responses from the first block to the second and the third block in both Bivariate groups. So pretty much participants got better as early as their second trial. Moving on to response time, overall, as shown in this figure, there were no significant decreases in response time between the two groups. So sometimes interactive features can slow down users. That's not what we saw in this case. It also didn't speed them up. So essentially adding an interactive tool didn't change response time. We were, however, curious about differences between fast and slow responses. Instead of looking at probabilities, we calculated the average number of area of interest transitions between slow and fast responses. So slower responses on the left, had almost 3 times the number of transitions between the map and the legend compared to the fast responses. So further research would probably have to go into this, but we hypothesized that perhaps faster responders had just internalized the legend more, and so they didn't need to transition to it as much and decode it before going to the map itself. Another thing that might hint towards that is that slower responders on average had more transitions between the legend, tooltip, and axis labels, so they were engaging with the legend a little bit more. Another thing to note is that overall response time also improved across both groups, both bivariate groups. And here it's also interesting to see how the interactive group catches up by the third block. We've noted how objectively accuracy and response time improved for both of our bivariate groups, but what did the participants think of that? Well, in our self-reported measures, we see significant decrease across all perceived workload metrics. This is the NASA TLX. It's not shown here, but perceived performance had also significantly increased by the third block. I should also mention that the univariate group had less linear changes in their perceived workload. So, what did we learn? Juxtaposed univariate Choropleth maps were just as effective for tasks that involved decoding specific values or patterns directly from the map, so tasks 1 and 3, noting a similar accuracy and efficiency to the bivariate group. So for these experiments, map suitability really varied by the intended task. However, in our anomaly detection and value comparison tasks, bivariate users were much faster and just as accurate. From an eye tracking perspective, bivariate users spend most of their cognitive effort in decoding the bivariate legend, whereas univariate users just had to scan the interface more to complete certain tasks. This focus on designing effective bivariate legends was emphasized by the works of Olson as early in the 1980s. So here, empirically, we show that, yeah, most of the hard work with bivariate maps is decoding that legend. Self-reported measures improved in the bivariate group as participants initially found bivariate maps challenging, but reported improved performance and reduced effort with experience. That's it. We've got some time for questions.
Thank you for your talk. Whenever you're talking to someone who's, in a decision position for publishing a bivariate map for COVID response, like, is there a positive effect on mortality or with vaccinations? Like, if you're asking, is it okay if we publish a Choropleth map as a bivariate one? And they're saying, well, no, because it's hard to read. Like, what would you say now? Like, how would you respond to that now?
It depends. So the question was, what would I say to someone if they asked me about the readability of publishing a bivariate map? And I would say it depends. I have some examples of some of the maps that were used during COVID, and they were, here, I'll just pull it up. This was by the European CDC. I mean, this is incredibly difficult to read. And so the simpler, the better. From a usability standpoint and map reading, I would say less is more. So I would say it depends, right? It depends on what you're trying to show and how you're trying to show it.
Do you think they're effective and if designed appropriately to convey the message?
So great question. Here's one where it's vaccination rate and case fatality rate. This is a map I designed. And essentially in this animation, we begin on January 1st, 2021. Vaccines aren't readily distributed until early May. Visually, in many regions, creeping blues are muffling the dominant reds. Essentially, as vaccination increases, case fatality decreases. Eventually, year in, we have what seems to be herd immunity in early 2022 until the next surge. So this is how I started my research. I thought, man, this is cool. It'd be so interesting to show it to people. And my committee very wisely said, whoa, that's too much. Let's bring it down. Because really, we have 5 dimensions here with 16 groups, right? We have geography, we have variable 1, variable 2, their relationship, and time. So that's 3,200 counties over 1 year worth of data. That's a lot of change blindness for people to go through, which is why we went with like one map to start with. Were you on my committee? That was literally one of their questions. Yeah, so we're University of Iowa, so we did not use Iowa. We ended up using Nebraska for COVID, and I actually have another slide if time permitting, but what we essentially did was we grabbed Nebraska with real data, interpolated it over 2 other similar states like South Dakota and I believe Kansas, and we did a centroid comparison to find like the nearest neighbor. So we did the same task 3 times over with simulated data, but similar distribution, so the distribution wouldn't change. But yeah, we did consider that, and part of our screening question had a, how familiar are you with US geography? So it was this one for the skill assessment. So we did consider that, but didn't find any differences. Thank you.